Hello everyone, this is Abdallah Kasir from ADAX, and today I'll be showing you how to run the TFAT nonlinear fracture mechanics tutorial. Okay, so the tutorial is for a simplified model of a valve bridge with 3 thermal cycles, each thermal cycle having 2 minutes of heating up and 1 minute of cooling down. Okay. So I would like to note that this video assumes that you have already run the finite element analysis of the model, and you have also run the TFAT DTMF analysis with the crack front approximation. Okay, so let's go ahead and jump straight through. Okay, so we start TFAT NLFM. Okay, just wait for it to show up. Okay, so here's the main window of the application. Alright, so as you can see here, we have the parameters that you can set. This is the viewport, some shortcut buttons. Alright, so we start by pressing File, Open TFAT CFG files, because we are opening a TFAT job. We go to the folder tutorial, and we select the CFG file. Okay, press Open. So as you can see here, we have the model, the simplified valve bridge model that we want to insert a crack in. Alright. Okay, so first thing that the user needs to do is to select the hotspot, select hotspot 1. Okay, let's bring it to the center. Okay. Right, then we need to specify the submodel. Okay, we need to define our submodel, which will be used for our simulation. Okay, so we will not be running a full simulation of the whole model, but of a submodel, of a much smaller submodel. All right. Okay, so we have, that makes things go faster. Okay, so we have two options. We can either have a rectangular submodel or a spherical submodel. So we will choose a rectangular submodel in this case. The center offset is used to shift used to shift or translate the submodel. So if you don't want the rectangle centered at the hotspot, you can choose to shift it in X, Y, or Z. The local X direction and the local Y direction are used to change the orientation of the rectangle, but in this case we'll just leave it aligned with the X and Y axes. Okay, and then the span of each dimension allows us to specify the size of the submodel. So by span we actually mean the half length. Okay, so we'll just enter 20 for each dimension. So that means we have a cube of side length 40 millimeters. Okay, effectively that's what it is. So we press show, we can see our submodel intersection with the model, the valve bridge model. Okay, after that we press apply. Okay, now the second set of parameters that we need to specify are the meshing parameters, or the mesh parameters. Within the mesh parameters we have the initial crack size. So this is the length of the crack. So crack size of 1 means that we have a crack depth of 0.5. So this is the entire length of the crack. Okay, and then next we specify the element size. So this is the target element size of the remeshing of the submodel. We just enter the number 3 because we know it works for this case. The third parameter is the crack resolution. So this is the target element size along the crack front, for the elements along the crack front. So you need this to be fine enough to get accurate results along the crack front. The fourth parameter is the tolerance. So we enter 0.01. So the tolerance is a generic tolerance parameter. It's used as the minimum element size. It's used as the starting separation between the crack faces and other things as well. Okay. Fine region is the radius of the toroidal region around the crack front, which is going to be remeshed to the resolution specified here. Okay. Alright, so then we move on to the analysis parameters. So we need to choose our material file. So we press browse and we choose this IMP material file. Okay, then we enter the abacus command that we are going to use for our finite element simulation of our submodel. So this is the command that you would enter from the command line to run an abacus simulation. Okay, then we specify the starting increment for our simulation. So in this case we're starting from scratch, so it's going to be 0. If we had a previous job, we could start from another increment that we have already reached before. Okay, then we choose the number of increments that we are going to run the simulation for. So we're going to enter the number 40. Right, so we know that this is sufficient to allow the crack to propagate through almost all the valve bridge. Okay, and then we specify the number of threads that we're going to use in our analysis. So if you have more cores, you can specify more. Now this parameter that we have reached to right now, so the abacus global model L set, so this is used to save time in interpolation from the submodel to the global model. Okay, so if you want to save time, you can tell it to just look in this L set. Alright, but for our purpose we just leave it empty. Alright, so the steps needed for submodel simulation. This allows you to select a subset of the entire simulation steps of the global model, so of the whole model. Okay, so suppose you have steps that you don't need, such as assembly or disassembly. You could skip them out, but in this case we're just going to enter all the steps. So like I said before, so we have 3 thermal cycles, and each cycle has heat up and cool down. Alright, and then the last parameter is used to specify the steps that are going to be included in the stable cycle, which is going to be used for the delta J computation. Okay, so the delta J computation will only be used for these steps. Okay, and then the final set of parameters that we need to specify are those pertaining to the crack propagation law. Okay, so we have the cycle skipping multiplication factor. Okay, so after each crack insertion and finite element simulation, we compute the delta J, and based on that we compute the delta A, so which is like the crack advance, how much the crack should advance. Okay, now but you know, this, if we want to only simulate one cycle at a time, it will take forever. So we need to assume that, you know, for each computation the conditions will remain the same for a specific number of cycles. So this is what you specify in this box here. Okay, so we're going to enter the number 1,000. So we are going to assume for 1,000 cycles the conditions stay the same. All right, so that's our upper limit. We also need to specify the crack growth law coefficient. So we have a coefficient and exponent. So for a Paris-like crack propagation law, and we also enter the exponent 2. Okay, now the second limiting factor for each cycle is the maximum delta A, so the maximum crack advancement. Okay, so I will enter the value 0.2. Now for after each simulation, the amount of advancement is limited by these 2 factors, by the cycle skipping factor and the maximum delta A, whichever limits more. Okay, so if you have a very large delta A, if you have a very large delta J value, all right, then your calculated delta A will be large, so you have to limit, you have to reduce your delta A value to the maximum limit specified here, and as an effect, your multiplication factor will go down. All right. However, if your delta J value is very small, then even 1,000 cycles might not get you to your maximum delta A. So the multiplication factor in this case will be the limiting factor. All right. All right. So now we've set all our parameters, and then we can go on and prepare the template IMP file. So the template IMP file is the IMP file that will be used for each crack propagation increment. Okay, so we press prepare IMP file. So we had a file from before, so we just press overwrite. So if it's your first time, you will not get that. Okay. Just wait for the editor to show up. Okay, so here's the editor. So in this case, so here you have the freedom to add whatever options and features that you want. Okay. So in our case, we could not retrieve the initial conditions from the ODB file. So we need to enter them manually. So we enter initial conditions manually here. So assume for all nodes the temperature is equal to 20. Okay. And we also add the creep strain tolerance. Okay, for our viscoplastic model. So we set it to 1e minus 4. We add that to each step. Alright. Okay. We press save. Okay, we close this, and now we are ready to run our simulation. Okay, so let's go. Press start analysis. Okay, so here in the log window you can see the progress of your simulation. So the simulation starts with crack insertion and meshing. Once that is done, it will start the finite element analysis of this submodel. Okay, so we'll wait for this to finish, and once it's done, we'll come back and we'll see our results. Now, throughout the simulation, as you know, you're progressing through the crack increments. Okay, at any stage that you want to see the current progress, you could just press the reload button, and it will reload any available results up to the increment that it has completed successfully. Okay. All right. So we'll come back once the results are finished. All right, and we'll see our crack propagation. Okay. So once the simulation is done, we press the reload button here to get the results shown on the screen. In the bottom section here, we have the delta J results plotted along the crack front from the start of the crack front to the end of it. Okay, it's shown for all the increments. Okay, from increment 0 all the way up to increment 40, and for each increment, okay, we have 5 plots from D1 to D5. These correspond to increasing number of element layers used in the computation of delta J. Okay, so in the viewport here, we have the von Mises stress contour for the submodel, and we also have, shown in gray, the simplified Weld bridge model, okay, which we can hide with this slider like this. Okay, you can zoom in, and here we see our initial crack. In this section here, we can step through the crack increments, these forward and backwards buttons. Okay, can go back to the beginning. This button here, we can animate the crack. Okay, the animation runs all the way to the end. Okay, and if we rotate our model to this view, okay, and then we press this button here, you can see the crack front contours color coded according to the number of cycles with this color map shown here. Okay. Alright, now we can also plot the crack depth versus the number of cycles. So we get 3 plots, one green, one blue, and one red. So the green line is for the center line of the crack. The red and blue lines are for the surface paths of the crack tips. Okay. Close this. You can also plot the delta J versus the number of cycles, but this is only shown for the center line. Okay. As you can see, the delta J begins at a low value and increases around 1300 cycles, then it drops down again. Okay. When it reaches the larger thickness area. Okay. Alright, so thanks for watching this tutorial video, and I'll see you next time. Thank you. Bye bye.